Hi, this is Dr. Walter Leite, and in this video, I will demonstrate how to run a regression analysis using R. For this, I use a data set from the Early Childhood Longitudinal Study, kindergarten cohort from the US Department of Education. First, I need to load the data set. What I have here on the screen is RStudio, which is the best interface to work with R. And the background is blue because I'm using the Cobalt font screen. Now, what I will show you is first reading the data set, which is saved in the same folder that this code is related to. And I'm running this on a Windows machine, but it should be similar for a Mac. The first thing I should do is set the working directory. The easiest way to do that in RStudio is to click on Session, Set Working Directory to Source File Location. Source file is the file I currently have open. So it read this command here, setwd. So at the bottom here, we have the command screen that shows all the commands I just run. So setwd sets the working directory, and this is where the data is located. Now, for every reading data command that I run, it will look in this particular director. Now we have the data set here. It's a CSV file. I'm going to run the read.csv function to read the data set. So I selected the line and I'll click on run. And I could have accomplished the running with Control Enter instead of clicking on run. And here in my environment window, it shows my data set. If I click here, I see the variables I have. The data set is in the environment as a data frame, which is a type of data in R. And I have the variable names with the class. Factor means it's a categorical variable. Numeric is continuous, integer, single numbers. Now, I can also see it by clicking on the object name in the environment. So here I have the actual data set. Now, I have some variables here, as you can see, that are 0 and 1. These variables are representing a categorical variable. So in R, it's ideal that these are coded as factors. But right now, if I click here, I see that these variables, such as P1 disable, is an integer. So first thing I will do is convert these variables to factors. I will do that with the command factor. So in this line, I'm converting three variables: disable, which is whether the child has a disability; W1 poverty, whether the child is above or below a poverty threshold; and P2 SGP farm, whether the child comes from a two-parent or single-parent family. And I will use factor to convert the 0, 1 to a factor labeled not disabled and disabled. So I'll select this, click run, and do the same for the others. Now, if I click here, I can see that it says that this variable is a factor, okay? And if I want to check the frequencies, I can type summary data, which is the name of my object. And I can see here that, for example, for P1 disabled, I have 2,594 disabled, not disabled, and 396 disabled. For the continuous variables, I have, mean, median, and other information displayed. Now, for this regression example, I will address these research questions. Over here, does mathematics achievement in kindergarten differ between students above and below poverty? Does mathematics achievement in kindergarten differ between students with single parent and students with two parents, and other questions here? Note that all these questions have mathematics achievement as an outcome. Therefore, I can run a single regression analysis to answer all of them. To run the regression, I will use the function LM in R, which stands for linear models. I will run LM as it's shown here and assign the results to the object that I will call regression. The name of this object is arbitrary. I decided to call it regression. Now, I have here two arguments for my LM function. I have the equation, this is the regression equation, and I have the data. These are only two of many possible arguments for the LM function. If I want to see a complete list of arguments, I can click here right in front of the parentheses and click on tab, and I see the list of arguments. Note that formula is the first one and data is the second. I did not name the arguments here, but if I named them like this, I would be in data equals data, I would be able to provide them in any order, but because I did not name them, I have to follow the order that is shown here. Okay, so for formula, I have math achievement. This two here is, this is the same as an equal in a regression equation. And then I have the predictors. Now note that this is a linear model just with main effects of the predictors. There are no interactions or polynomial terms, but I could add those if needed. I will now run. Note that here in the output that my model ran no warnings. I want to see the results now, so I'll use the function summary, which is very helpful to get results for many model fitting functions in R. And the summary regression, I will output it to an object called results. So that object, now currently I have two objects in the global environment, data and regression. I will run line 35 and I'll get results. And it has many things inside of it, residuals, coefficients, R squared. Now I want to print it in a neat way, so just call its name here, and it printed on the output window, which I can click here on the corner to see. So these are my results. You can see the regression equation is here, a summary of the residuals, and then I have the estimated regression coefficients, standard errors, t-value, and p-value. Notes that, so the intercept is the expected value of the outcome when, for the reference category of the, by categorical predictors, and when the continuous predictors are zero. So it's not, here it's somewhat interpretable, so it'll be when hours of non-parental care is zero, number of siblings is zero, SCL is zero, and number of hours watching TV is zero. But the intercept, usually you can scale your data to make the intercept mean different things. Now, the next coefficient is for the variable single or two parent. Now, R does automatically decode if the predictor is a factor. So we took the first category, which was two parent, as a reference category. So this coefficient here is the difference between households with single parents and households with two parents. It's a negative coefficient, however, it should not be interpreted because it's not statistically significant. Now, the second coefficient, similar because it's a categorical variable with two categories, it took below poverty as the reference category. So here we see the effect of above poverty. So 2.303107 is the difference between children, the expected value for children above poverty and the expected value for children below poverty, and that's statistically significant. So children above poverty have a mathematics achievement that's on average 2.303107 points above children below poverty. Now, for the continuous variables, which are these, we have regression coefficients here. For hours on parental care, it's not significant. For number of siblings, is also not significant. SES is significant. So 4.10 indicates that for each increase in 1 point in socioeconomic status, you would expect an increase in 4.102261 in mathematics achievement. Another way of thinking of this is that the expected difference between children of a certain socioeconomic status and children with 1 point higher socioeconomic status is 4.102261. Okay, and the coefficient of number of hours watching TV is not significant. Now, it also shows some summaries, some interesting information here. We have both for R-squared and adjusted R-squared. For the adjusted R-squared, for example, it would mean that 17.9% of the variance in math achievement is accounted for by the predictors. The F statistic indicated that the predictors significantly account for variance in the outcome. And so this is an omnibus test for the whole model. Okay. Now, we can get some other information. If I use the function ANOVA or the object regression that I saved, I can get the ANOVA table, which gives me the sum squares, the mean squares, and F value for each factor, whether it's significant. And I can use that ANOVA table to calculate different effect sizes like eta squared, partial eta squared, omega squared. But here I'll just show you how to calculate the R-squared that's already reported in the summary. So I will take the sum of the sum of squares and divide it by the total sum of squares and assign to this object called R-squared. And you can see that I get the same as the unadjusted R-squared. All the extraction functions that are helpful to operate on the regression object is resid, which gives us the residuals. Fitted gives us the predicted values. And like, for example, if I want to plot predicted and errors, so errors as a function of predicted, I can plot, and here see that if I click on zoom, I'll get a better view, and you can see that there is mostly not a relationship between errors and predicted values, which is what you want. And then something else you could do is do a diagnosis of multicollinearity using the package car. Here I already installed it, so I don't need to run this line. I can call the library car, and I can run the function of VIF to get the variance inflation factor. And I would be concerned if it was more than 5, but here these are low, so it indicates that I don't really have a problem with multicollinearity with this data set. So that's it. That's how you run regression in R.